Yeah, my I disabled that initially. My wife still has it though, I think. Yeah. Yes, but not to me. Yeah. But there was a time when you needed when like you went to Italy for a while, you needed to be able to like plug into the phone network and dial up, get a modem, and AOL had a network of local dial-ins. So this is left over from those days. It's a long story. But now I just keep it for kind of retro geezer chic. Okay. So I guess the title pretty much states the main result of the paper. So this is basically all you need to know. Homogeneity and pure state continuous reversible transitivity characterize Jordan-Algebraic general probabilistic systems. So I'll spend the rest of the talk both defining these terms so that you actually understand what this means, and also motivating some of these properties. In fact, I'll spend quite a bit of time on motivating why they might be interesting properties of a physical system. So this is part of a research program which I guess most of you have been introduced to. The idea is to study information processing and what physics might be like in a general probabilistic framework that's encompasses the way we think of quantum theory in quantum information, but is quite a bit more general. And there are various things we do in this program. One is to try to characterize quantum theory or even classical theory within this broad framework in terms of various postulates or axioms. Maybe these postulates have to do with information processing. Maybe they're related to physics, like what would thermodynamics be like in a particular, given particular principles that could be formulated in this framework. And also even just mathematically natural properties often come in. And even though people sometimes criticize particular results as, oh, that's so mathematical and we don't understand the physical meaning of these assumptions, it often turns out that you can elucidate the physical or information processing meaning of mathematical assumptions. So it's good to, when you see a mathematical derivation of, say, C-star algebra state space, like that by Alfvén and Schultz in the 70s, think about its physical significance. It's also interesting to understand, of course, the landscape of other possible theories, where quantum theory lies in it. And just a reminder, what we're thinking of a theory here is more or less a kinematical description maybe of quantum state space in terms of, states are density matrices, measurements are POVMs, dynamics are CP maps. That's what we're abstracting. And in real physics, there are actually preferred observables like maybe position and momentum, and you've got space-time, and the thing isn't necessarily a monoidal category where Alice and Bob send systems back and forth, and Charlie and so forth. So it's just good to keep that in mind. I'll have to manually switch the slides, I think. Okay, so why do this? I think maybe I won't go into a lot of detail about the motivation. Jamie said some good things about it the other day. So let me say a little bit about the framework more formally. So as you probably remember, the normalized states are a convex set. That's the density matrices. So maybe, of course, that would be the block ball for a qubit. In real quantum mechanics, it's just a disk. I don't know if you have a 3-state classical system, it's a triangle. Okay, and normally we stick it in one higher dimension. So, convex sets naturally live in a real affine space. We stick it in one more dimension, and we use it as the base of a regular cone of unnormalized states. In quantum theory, those are just positive semi-definite matrices. It's handy to have those around. And one of the main reasons it's handy is if you represent dynamics in this framework, you might have different things happening to the system depending on the outcomes of some measurement or test, and the probability of them happening will actually be described by the norm of an unnormalized state that comes out of a process. It can be interpreted as the probability of that process happening. Okay, so since this is a cone over a convex compact set, we have a regular cone. It's topologically closed, generates the whole vector space. It's pointed. So I mean, here it is for a real qubit, a rebit, right? It's just a Lorentz cone in 2 space and 1 time dimensions. You can think about it. Of course, the dimensions aren't actually space and time. You know, this cone of a classical trit, it just looks like the positive orthant in R3. Whoa, it's working. Okay, it just took time to download the whatever drivers. Okay, I thought, well, yeah, okay. All right, and then having this positive cone makes this ambient space. So this is a real vector space. I usually just use the name of the system as the name of the vector space. Makes it an ordered linear space. So, you know, if the difference of 2 things is in this cone, we say the first thing is bigger than the second thing. And you can add inequalities and you can multiply them by positive scalars, just like inequalities between real numbers, which are, of course, an ordered linear space where the positive cone is the non-negative real numbers. Okay, measurement outcomes are just functionals on this space, linear functionals to the reals. We call them effects. And the important thing is their values in on normalized states have to be probabilities. The unit effect actually slices through the cone, the plane u equals 1. This is what I think Jamie called the throwing away effect or something. The unit effect slices through the cone, the plane where it's 1 slices through the cone and gives you this base consisting of the normalized states. So these effects obviously lie in the dual vector space, as I've formulated it, since they're functions to the underlying field. And the set of all effects is just, so the dual vector space, of course, has a dual cone, which Jamie talked about. It's the set of all functionals that are non-negative on everything in the primal cone. And the set of all effects is just the interval in the dual ordering between this unit effect and 0. So for this situation, the dual cone actually looks just like the positive cone. This is a rebit. And this order interval actually looks like this. So here's U. Here's the rest of the dual cone. So it's this double cone. For this, it's actually a cube. The set of effects is actually a cube. Okay, and then measurements, we just take a set of effects that add up to the unit effect. Just like in quantum theory, you know, the effects are just trace it, you know, multiply your state with a positive operator, which is a POVM element, and then take the trace. That's the linear functional, that's the effect. And if your positive operators add up to the identity operator, those effects add up to the trace functional, which is what we use to normalize the states. Okay, you can, if you want, restrict measurement outcomes to a convex subset. If you have an effect, you should have the unit minus the effect, so you can make it at least part of one complete measurement. And maybe, as Jamie mentioned the other day, you could choose a subcone of the dual cone and just look at the unit interval in that dual subcone and that subcone of the dual cone, and let that. I think we'll let that be your effects, but we'll usually assume no restriction in this talk. Okay. Another common way to formulate these sorts of theories is instead of explicitly talking about the dual space, okay, I'm going to be in finite dimension the whole time. So the dual space is isomorphic to the primal space, and instead of explicitly referring to the dual, we just pick any positive definite inner product on the primal space, and we can say represent it internally, represent the dual space as the primal space. Because taking the inner product with an element gives you a linear, that's a linear functional. So the internal dual, which is dual cone, which is isomorphic to the dual cone in the dual space, is just the set of things that have non-negative inner product with everything in the primal cone. So fine. Now, if you can find an inner product relative to which this internal dual cone is equal to the primal cone, then we call the cone self-dual. It's a very strong condition on cones, and in particular, it's important to notice it's stronger than weak self-duality, which is that the cone is affinely isomorphic to its dual cone. So if I have people like PR boxes, the state space of one wing of a PR box can be thought of as a square, because there's basically two, you're thinking of specifying the probability of two measurements. And so you have this cone over the square. The dual to that cone is also square-based. It's linearly isomorphic, but it's rotated 45 degrees. And there's no way with a positive definite inner product to get a dual cone that's not somehow rotated with respect to this thing. So weakly self-dual but not self-dual is definitely. Okay, I guess. I mean, how can you prove it? I mean, I'm not absolutely sure how to prove it right now, but I mean, I guess you would just write down any such, write down the isomorphism, and somehow you diagonalize the thing and you see that the signature, that it's got a negative eigenvalue, I guess, is the way to think about it. That's probably what's going on. So, I mean, if you allow not positive definite inner products, like a Lorentz product, you could get it to be the same, but it's sort of not the usual way we think about formulating these things. Okay. I guess an important concept is going to be reducibility. So we say a cone is reducible if it's the direct sum of two cones. So these are two subspaces that are complementary. They only intersect in 0. And every extremal ray of the cone is either in one or the other of these sectors. What's an extremal ray? Well, the base has extremal points. We call those pure states. Those are the elements of this convex set that cannot be written as non-trivial convex combinations of other points in the base. And an extremal ray of the cone is just a ray that's generated by an extremal point at the base. So there's a one-to-one relationship between those. And actually, for faces of this state space, there's a one-to-one relationship between faces of those and faces of the cone. So faces are like, this is the face, that's a face, the whole thing is a face. They're closed under including, if you have something in the face, you can make it as a convex combination of things in the cone or in the convex set, then the things you used to make it as a convex combination also have to be in the face. Most faces we're interested in are going to be exposed, which means they're the intersection of the convex set with a supporting hyperplane. So like this, like that, and then we have, I don't know, the degenerate hyperplane. Okay. So the point is, if a cone is reducible, the two components into which you separate it are like superselection sectors. There's no coherence between them. Which sector is classical information? You can get that information without disturbing states in the cone, for instance, or states in omega, normalized states. Okay, every finite dimensional regular cone decomposes uniquely into some irreducible summands. I mean, uniquely maybe up to relabeling. Okay, so basically when you're trying to characterize GPT state spaces, if you characterize the irreducible ones, you've pretty much done the job, because then you can just classically, you just have a bunch of different classical sectors, and it's pretty clear how that works. Okay, dynamics. We want a you might want a semigroup of positive maps, say from one system to another. So it should take the positive cone into the positive cone, and that should be a B, obviously, if the system's not identical. If you want them to be have this physical interpretation where the norm, which is just the value of this unit functional on the state, is interpreted as the probability of undergoing this process, then you should want the norm, you should want this map to decrease the norm. All right, so this just generalizes trace non-increasing positive maps in quantum theory. Now I see, yeah, I didn't include this. Okay, I didn't include a summary of the. There we go. I don't know why I think pointing at the screen should make it work, but it works. So, and just a note here, it's often nice to formulate theories where you have a bunch of systems as a category, and then you have, you know, of course, categories, you have morphisms, and you always have composition, which we think of as sequential, one process after another. In a specific monoidal category, which is what you usually use in the GP setting, you have a way of making composite systems, which you represent by this tensor product symbol. That's the monoid operation. That's where the name monoidal comes from. We make symmetric. Monoidal refers to the fact that this is symmetric. So A composed with B is the same as B composed with A. And you know, it's nice in a lot of ways. It enforces complete positivity in the quantum case. And we might actually generalize the notion of dynamics to just say that, I think I used the wrong slide here. Yeah. Yeah. Okay, so a nice way to do it is to think of things as enriched over ordered linear spaces, which basically means that the set of dynamics from one system to another, it is indeed a cone, and it's a semigroup, which follows from having a category around. You have to have composition. But you might actually have two different dynamical operations that induce the same positive map between the state spaces of A and B. And the reason you might want to do that is because when A and B are part of a larger systems, you might actually be able to tell the difference. So it looks like they're doing that. You can't tell the difference when you just act with these two things on one system, but actually they do something different in the larger world. So category theory can take care of that nicely also. Okay, norm preserving just generalizes trace preserving. It means you take normalized states to normalized states. Instrument, we have the same ideas in quantum theory, a bunch of dynamics that sum to norm preserving dynamics. We call dynamics reversible if it's an operation that takes the normalized states onto the normalized states. So in quantum theory, that's rho goes to u, rho, u dagger. And actually also the transpose is reversible. We don't include the transpose because it's not completely positive, but it's certainly a reversible automorphism of the state space. Okay, so that's the affine automorphism group of the normalized states. There's also, we're going to be interested in the automorphism group of the cone. And that's the linear maps that take the cone onto itself. Okay, so because they take the cone onto itself, they're invertible, and the inverse also preserves the cone. So it's a good dynamics. Okay, and these are often called order automorphisms. Okay, I guess I'll say aught0 is the connected identity component of this group. Okay, so here's an important definition because it's one of the main properties that is occurring in the main theorem that I'm going to be proving. A is homogeneous, so A plus, the cone, is homogeneous if its automorphism group acts transitively on its interior. That means for any two interior points, there's an automorphism, so X and Y, in the interior of the cone, topological interior, there's an automorphism that takes X to Y. So the interior of the cone is a homogeneous space for this group. Okay, Winberg showed in the early 60s that the dual of a homogeneous cone is homogeneous. It's nice to know. Another thing that's been shown is that every homogeneous cone is actually can be represented as a slice through some positive semi-definite cone in higher dimension, possibly much higher dimension. And you could use the cone of positive semi-definite real symmetric matrices is typically what they use. The second statement. You can represent every homogeneous cone as a slice of an SDP cone. Yeah, that's not trivial to prove. I mean, I'm not sure exactly when it was proved, but I think Chua and Tunsel proved it sometime maybe in the 90s, early 90s, and there may have been some other independent proofs. Yeah. How do we get the what? From the PSD cone? Oh yeah, sure. So you just slice through, you know, well, let's say you have 3 by 3 Hermitian matrices. The diagonal matrices are subspace. That's your slice. I mean, that's an example. You know, here is the simplest homogeneous cone that is not, well, that's not Jordan-Algebraic. Let's see if I get it right. I think it, you'd have alpha 1, alpha 2. I don't know. These are real, so let's just put beta and beta. I think you'd have alpha 1 and maybe gamma 0, 0. This is due to Vinberg. So you take the intersection of this linear space of symmetric matrices with the positive semi-definite cone, and that is a homogeneous cone that is not literally a cone of positive semi-definite matrices. And its dual lies in this, has the same form, but obviously it's not, again, the intersection with the positive semi-definite matrices. It's a little bit bigger, and you can describe it with some polynomials, but not all the polynomial constraints that would get you positive semi-definiteness. Okay. And so there are various different ways of embedding things into PSD cones, different dimensionalities. I mean, there's one way that basically just, you know, involves sort of putting in some zeros and stapling in some elements that have to be the same. Okay, I mean, I think it is instructive and interesting, and there's a lot more to be done, and somehow it's even related to graphical models by some statisticians, and they use these things to generate exponential families of distributions, and I don't understand that literature, but you know, some of you who are interested in graphical models might want to look into it. Right, so let me just say how quantum is homogeneous, and then I'll go back to the statement of the theorem that I had at the beginning. So the interior is the non-singular of the quantum cone is the non-singular positive semi-definite matrices, i.e. the positive definite matrices. And this Txy that takes a given matrix X to a matrix Y is just this map. It takes whatever matrix you put in, sandwiches it between X to the -1/2, which is positive semi-definite, so we don't need to take a dagger here, and sandwiches it between Y to the 1/2. Obviously, if you stick X in there, you get Y. So that's the proof that it's homogeneous. Now this, so these are just the Krauss, if you want to think of the Krauss maps with non-sync, okay, one CP maps that have one Krauss element, and the Krauss element is non-singular. Now this actually isn't unique. If you want a unique map that takes X to Y, that's a simply transitive action. There is indeed a group that does that. It's a triangular subgroup of automorphisms. And basically, in the quantum case, it's just the Cholesky decomposition, right? So you can take T to be the non-singular lower triangular matrix with a positive diagonal. That is the Cholesky decomposition. Well, okay, so I should... Yeah, let's take this map. This map will take the identity to TT dagger. TT dagger of this form covers the interior of your cone once. And then if you can take the identity to anything, the inverse will take any other thing to the identity, where you adapt it to the thing you're trying to get to the identity. And so you can get from anything to anything else. Let's just say it's triangular in some basis. But there is a definition of triangular group in group theory, and this thing is a real Lie group. So, you could use that. And again, it's going to have to do, for this type of groups, with being able to find a faithful representation in which it's represented by triangular matrices. Okay. All right. Yeah, I guess this is the one more thing we need in order to state understand the main theorem. So Jordan-Algebraic systems, introduced by Pascual Jordan in the early 30s. Jordan-Algebraic, it's a non-associative real algebra, but it abstracts properties of the Hermitian operators. So he actually introduced it because he thought it might be a nice algebraic way of formulating quantum mechanics. And I think this may be the guy who actually told Heisenberg and Born about matrices, and that indeed, right, the Dreimanner Arbeit was Jordan, Heisenberg, and who was the other guy? Born or Schrödinger? I don't remember. But anyway, symmetric product abstracts. So it's of course a bilinear product. It abstracts, just the symmetrized multiplication of matrices. And it's not associative, but it satisfies the Jordan identity, which is a special case of associativity. He wanted them to be formally real. So if you have a sum of squares that's 0, 2 squares summed to 0, each element that's being squared is also 0. And the reason for this is so the cone of squares in this algebra will be pointed. Pointed basically means it intersects its negative in 0. And you want it to be pointed so that when you slice it with this normalization functional, you actually get a decent state space, so that it's convex. Right? If the cone isn't pointed, you could have a wedge, you slice it, and you get this infinite strip. That's not going to be a good state space for a probabilistic theory. Okay. So a theorem by Kocher and Winberg, independently, says that the irreducible finite-dimensional homogeneous self-dual state spaces so self-dual cones, are all isomorphic to the cone of squares in some Euclidean Jordan algebra. Sorry, Euclidean is a synonym for formally real in finite dimension. Now, I just want to note, there are many weakly self-dual homogeneous cones. Ishii, I think, gave the first example in maybe the 90s or the early 2000s. And there aren't very many of these homogeneous self-dual cones. You're quite close to quantum theory when you have them. They're just the self-adjoint matrices over R, C, and the quaternions. And of course, the cones of positive semi-definite matrices in those. The spin factors, the positive cones are Lorentz cones, just cones whose base is a ball. You can think of them as light cones in n space and one-time dimension if you want. And this weird 3x3 self-adjoint octonionic matrices, the so-called exceptional Jordan algebra. And that's it. So frequently when you are trying to characterize quantum theory by some postulates, you get here, and then you need one more thing to get the complex field. So an example of a thing that works is something that Cosmin Uderdek and Marcus Mueller and I used in a paper from 2014, which is in New J Physics, which we called energy observability. So we wanted there to be continuous reversible dynamics, so we have a non-trivial Lie algebra, and we wanted the generators, well, the elements of these Lie of this Lie algebra, which you can think of as, we were thinking of them as energy because they generate dynamics, one parameter reversible dynamics. We wanted them to be able to be injected into the observables of the system. The observables is just the vector space spanned by the effects. And we also wanted the observable, the image of a generator of dynamics to be conserved by the one parameter family, of transformations that it generates. So it's kind of a Noether-like rule. So we called that energy observability. And that actually picks out quantum systems over the complex numbers. There are other ways to do it. It's hard to combine these things in a locally tomographic way unless they're all complex. I'm not exactly sure what, well, Alex Wilson and I have one theorem to that effect that says if you, given some conditions, anything that can combine with a complex has to already be complex. I think there are probably other no-go theorems that are even stronger. Okay, so I won't say more about how to get complex quantum theory out of Jordan-Algebraic state spaces. We're now going to be just thinking about how do we characterize Jordan-Algebraic state spaces. Once we do that, we've got a couple of ways of getting complex quantum theory. They already have, of course, continuous reversible transitivity. They're, of course, homogeneous, as the theorem on the previous page implies. And they're often called symmetric cones, basically because the interior is a non-compact Riemannian symmetric space, and they're the unique cones with that property. I don't think that's terribly important to us. So now I'm going to go back to the theorem at the beginning. Right. So here's the theorem. If a GPT has continuously reversible transitivity, so we're looking now at the automorphisms of the normalized states. They preserve normalization, and they're reversible. So if the connected identity component of that group acts transitively on the set of normalized, on the set of pure states, so you can take any pure state to any other pure state reversibly. So in quantum theory, that's true. Any rank 1 projector can go to any other rank 1 projector by sandwiching it between unitaries. Okay, that's continuous reversible transitivity. Lucian Hardy, wrote a paper around 2000 that helped kick off the interest in GPTs in the quantum information community, and this was one of the properties he used in that paper in his characterization of quantum state space. So it's a frequently used property in GPT theory. So my result, which is not, it's pretty much a corollary of some description of the automorphism group of these cones from the 60s, is that a GPT, and also the description of the structure of the cones, a GPT that is homogeneous and has continuously reversible transitivity on pure states is irreducible and Jordan-Algebraic. Okay, and as I mentioned, we have options for getting to quantum theory. Well, I'm imposing both. So, I mean, the 60s just described the automorphism group. This is by Vinberg, a paper on the structure of the automorphism group. And then there's also a description of the structure of the cone. And once you ask this question, is there continuously reversible transitivity on the extremal points? Because you have some description of the extremal points, you can look at how that goes with this description of the automorphism group, and you can see the answer is no. And so if I have time, I'll go into that, the mathematics of that a little bit, although it's pretty technical, so I don't want to go too deeply into it. Right, so this is the result, and I want to spend a little time motivating it. So like, why would we care about these properties? What do they imply, or what implies them that has some kind of physics flavor? And I hope you, I think I may have gone, some motivation, good. So I mentioned Hardy used it. So what motivation does that have? Well, there might be some thermodynamic motivation. And for instance, von Neumann used this. Von Neumann used the property in his argument that the quantum, or now it's called von Neumann entropy, should be the thermodynamic entropy. You know, he had something where you had a mixed state and you did measurements and separated. So I think he had a gas of particles and the internal degree of freedom was quantum, and you did some measurement on it and separated the particles based on the measurement result, and then you had some pure state ensembles and they had different pressures, and you moved some pistons and did some work or had to do some work, and this amount of work turned out to be given by the von Neumann entropy. But he had to assume that all the pure states were kind of equivalent. And so he made the argument that because you could get between them by this reversible transformation, we should think of them as thermodynamically equivalent, which seems reasonable. All right. Now, another nice thing about this property is that even the non-continuous version of it, so I just say the automorphism group acts transitively on the pure states, whether it has to be a continuous group or not. Well, you can see the square, of course, has reversible transitivity on pure states, but it's that the automorphism group of those states is not, it's a finite group. It's not, it doesn't have a non-trivial Lie algebra, so there's not continuous paths connecting those states. But even the non-continuous version enables teleportation in suitable composites. And it implies the existence of a unique invariant state. And, you know, it's basically like you need one state that will do teleportation, one entangled state that will teleport things if you get that measurement outcome. And then having this big group, the group can take you to a bunch of other states that will also teleport if you correct by the group element, and that gives you a complete basis of entangled states. And of course, the entangled state you throw in, it just corresponds to the one you always have corresponds to the identity map. And then if you have this big group, it gets you all the other ones you need. Now, I say you can do that. What you need is you have a system A, B, and then C, which is isomorphic to A, because if you want to talk about teleportation, you have to be able to say you got the same thing. So, you know, in goes your state here. Well, it's just the usual thing. You have some entangled state on BC. Your state goes in on A. Something comes out here. We're not guaranteed, well, so maybe after I talk about composites, I'll come back to what you need, what else you need to make this argument work. But so, I mean, there's a variety of nice things that are related to that. This is sufficient for teleportation, again, in suitable composites. Basically, you need a maximal tensor product and a minimal tensor product. If you're lucky, you can do it with with smaller tensor products, and if you're really lucky, you can make them isomorphic. Homogeneity. What's so good about that? Well, some people think that homogeneity is well motivated on the face of it, and they talk about, you know, the idea that with some probability you should be able to prepare any interior state from any other via automorphisms. It's not really clear to me why you would expect, you know, to be able to prepare via automorphisms. I mean, if you can't prepare a state, then maybe you don't want it in your theory. I could see that, you know, if your theory breaks up into inaccessible regions, you'd want to concentrate on one region. I don't know. So I didn't find this particularly compelling, although there might be some sort of Bayesian arguments for it, but you need to say a lot more. One thing I do like that Alex Wills and student Philip Gabler and I showed in about 2008 is that it enables steering of all interior states via composition with a dual system, and that's a system whose state cone is isomorphic to the effect cone of the initial system. And that's tightly linked to purification. And again, when I say it enables steering via a composite, you can definitely do it if you take the maximal tensor product. And again, if you're lucky, you have some smaller tensor product that just has the states you need to steer, maybe. Or right, like we know the maximal tensor product is in general very far from a self-dual situation. And so if you want some other nice property like self-duality, you know, these theorems about what you can do if you have the maximal tensor product, that's basically the situation with teleportation as well. The theorems, well, I mean, the theorems always apply, but they may not allow you to do teleportation with a particular composite that has some properties you want. Okay, and how might you motivate self-duality? Well, it sort of seems like a kind of time reversal symmetry. It's a very strong isomorphism between states and effects, but I don't have anything really deep to say about that. That's a very fuzzy intuitive feeling. And Alex Wills, my collaborator, actually did link it up with a nice property, which is if you have other things going on, including homogeneity actually, it's linked to the existence of a perfectly correlating state. So that's a state where basically if I make a sharp, fine-grained measurement on one side, there's always some sharp, fine-grained measurement. Those outcomes are perfectly correlated with it. So that seems like a nice and information-flavored principle. Okay, so these mathematical, beautiful mathematical concepts are also not totally off the wall in terms of operational meaning. So I could go more into the technical details of how you prove that theorem, the structure of the automorphism group, or I could go more into motivation. So and what I would do for motivation is talk about composite systems and steering, I think. So I don't know, what would people most like to hear? Okay, I knew you would say technical details, David. But what about the steering stuff? Motivation. Okay, so we've got both. So, all right. So, okay. I think what I'll do at this point, I will quickly summarize the technical details, and then I will try to get to the motivation as well. Although, yeah. So I'll try to be very fast, but I need an eraser. Here we go. So what Winberg did in characterizing the automorphism group was to just generalize. So he introduced the notion of a T algebra. Well, let's see. Tell you what, I'll try to do the steering first, and then we'll go quickly over the T algebra. I think that's better. So I'm just going to go over one motivation, which was this business of steering. So we've got composite systems. And it's just another system such that the tensor product is real vector spaces, is a subspace of the ambient space, and all the product space are in the positive cone of this system. All product effects are in the dual cone. I think this was formulated in case you had a restricted subcone of the dual cone C, which we'd call C sharp. But all product effects have to be in it. And the order unit, the unit effect, is just the product effect. And now we call the composite locally tomographic if this ambient space actually is the real vector space tensor product. And that means that expectation values of product effects actually determine a state. That's why we call it local tomography. Right? I mean, they give you the components in a product basics, basically. Okay, and then a composite is regular if conditioning works right. We're only going to care about two-part composites. Note this definition enforces no signaling between subsystems, so it's a good definition, reasonable. Examples: the maximal tensor product, all states positive on product effects. The minimal tensor product, we take the state space to be the convex hull of the product states. And if we wanted to define a system, let's just take the dual cone to be the full dual, no restriction. So one of them has only entangled, has no entangled states. The other has no entangled effects. All right. Any state has marginal reduced states. You just plug in the unit effect on one side, and then you get a map from effects on the other side to the reals, and that's a state. So there's this conditioning map, which is partial evaluation. So we say omega hat, which goes from A star to B. So this is a state omega AB. It just takes an effect on A. So this will give you this maps a measurement outcome on A to an unnormalized state, which we think of as the unnormalized conditional state, conditional on getting measurement outcome A. And of course, it just takes A to the state omega of A, and then you plug in the B thing there. Now, if omega hat is an order isomorphism, I'm going to call the omega an isomorphism state. For example, the maximally entangled state, any maximally entangled state. Actually, any full Schmidt rank state. Okay, steering of ensembles. So having unnormalized states makes it easy to represent ensembles because the probability we just fold in is the norm of the state. So if we have a bunch of if we have a state omega AB and a measurement f sub I, it always holds that the conditional states are an ensemble for the marginal state. The unnormalized conditional states add up to the marginal state. And then we say a state is steering for its marginal if for every ensemble for the marginal, omega B, there's a measurement fi on A indexed by I such that omega sub I is this unnormalized conditional state conditioned on f sub I. So we're steering to that ensemble. Okay, and I mean this, among other things, this defeats bit commitment schemes that are based on non-uniqueness of decomposition into pure states. Because you can steer to any ensemble. This was the original quantum no bit commitment argument, or part of, this was the argument against this type of scheme. Okay, so it's easy to see that isomorphism states are steering, like, for instance, the maximally entangled states in quantum theory. Okay, and there are some relations between homogeneity, steering, and purification. So the following are equivalent, and this stuff is all in this paper. It's in Foundations of Physics, and it was also on the archive in around 2009. Alex Wills, Philip Gabler, and I. So it's equivalent for A to be homogeneous, or for every normalized state in the interior of the positive cone to be the A marginal of an isomorphism state in the maximal tensor product, where this, where B is any fixed state space that's isomorphic. So this should be B plus is isomorphic to A star plus. Its unnormalized state cone should be isomorphic to the dual cone of the first. Because you see, steering is basically about getting a bunch of effects that add up to the unit effect over, so that's in the dual space, over to a decomposition of a state in the primal state, primal space. So we're going to want, if we want to be able to steer everything, we're going to want the space where we're using the effects to be isomorphic to the dual of the space with the states. Okay, and interestingly, if these conditions hold, then if you take any two states of the sort that are guaranteed here, so this, that should be the interior. So any two normalized states that have the same marginal, there's an automorphism on the additional system that takes one state to the other. So this kind of has the flavor of the purification axiom that is, for instance, used by the Pavia group. Okay. All right, and now there's an interesting fact. For irreducible systems, order automorphisms are pure in the regular cone of positive maps, and that means they lie on extremal rays. And so they're pure in fact, any composite state space in which they occur. And we assumed local tomography in this paper. I don't think it was really that important. It may be that most of these results don't use it. But the ones involving purification probably, it's probably crucial. So this is sort of not surprising, and you might think it's folkloric, but I didn't find it anywhere else. So now we see that if we have irreducible state spaces, this theorem is actually giving us something like purifications. So this construction gives us purifications, and they're related by a local isomorphism. So we have this purification axiom, at least for this composite. Okay, so let me quickly just get to some slightly more general statements about steering. So let's think about theories, and let's say we have universal steering if for every system B and state beta in the normalized state beta in B, there's some other system and a state on that composite of those two that steers this B marginal beta. And when I say steers, I mean you can get to any ensemble. And then we say there's uniform universal theorem steering in a theory if we can always use the same system to steer every state in B. So this is A sub B. It depends on B, but it steers every state in B. Universal self-steering if you have uniform universal steering with the two systems actually isomorphic, and bidirectional uniform universal steering if B also steers every state in A sub B. So then if we have universal uniform steering with them having with the steering system having the same dimension as the steered system, and this in particular is going to be true if the steering is bidirectional, then every irreducible finite state dimensional state space in the theory is homogeneous. And in fact, if there's universal self-steering, then they're not only homogeneous, but they're weakly self-dual. So you get some properties out. Well, this is one sort of motivation for homogeneity. All right, and then maybe I'll say a few things. Well, maybe about few things about the technical details, and then I'll try to leave the 10 minutes for questions. I think this was counting down from 50, right? Yeah. Okay, so. And maybe I'll just go back to the main theorem. Yeah. So Windberg defined something called a T-algebra, and he showed that homogeneous cones are the sets TT star in T algebras. That's a one-to-one relationship up to isomorphism, where T is again lower triangular positive diagonal. So it's like the Cholesky decomposition, but this isn't just an ordinary matrix algebra. It is what's called a matrix algebra with involution, so it's a bigraded algebra, which means it's made up of a bunch of algebras which you can arrange in a matrix, basically. So you have this IJ. Okay, so here we are. And all of the diagonal, well, make it square. All of the diagonal algebras are isomorphic to R. triangular matrices associate with lots of stuff. I'm not going to go into these associativity axioms, but let me just tell you what they are for a homogeneous self-dual cone. So basically, it's just the complex matrices, let's say, for the quantum situation, except that you project the diagonal into the so that they're real. You kill the imaginary part of the diagonal, and the multiplication is just do ordinary multiplication and then do this projection. So it's almost the full matrix algebra, but not quite. And since you have this involution, you can define a Hermitian part, and these TT stars are in the Hermitian part. Right, and so he shows that all homogeneous cones have this kind of representation. It's a Cholesky-like decomposition in the T algebra. And then it turns out that these T algebras decompose into, let's say, some blocks. So maybe these are two such blocks. And within each block, you have a homogeneous self-dual cone, a symmetric cone. And then the direct sum of these cones is called, let's say, VC, the kernel of the cone. And then there are conditions on what these off-diagonal algebras can be. I think basically if you have two of these things, you either have to have zeros or they have to be all the same. And so in this Winberg example that I didn't erase, right, you can see the upper 2x2 block and the bottom right one-dimensional thing, that's the kernel, and then there's this off-diagonal algebra. Okay, so in this algebra there are idempotents, and basically they're just ones in this algebra, and those generate extremal rays of the cone. I'm not going to claim they're all the extremal rays of the cone, but they are extremal. And so now we just need to know a bit about, basically what I'm going to claim is that the base-preserving automorphisms can't take an idempotent here into an idempotent there. And therefore, at least the identity component can't. And so therefore, we can't have continuous reversible transitivity. And to show that, we just need part of Winberg's description of the automorphism group, which luckily is fairly short to write down. And it's done in terms of the Lie algebra G of the full automorphism group. We split it into G0 plus GC plus something he calls TU. I have no idea why it's U here. Okay, this is an ideal, and it's triangular. So you want to think of stuff like the raising and lowering operators in the Heisenberg group when you think of this triangular thing. And what it does is basically there is some ordering of these sectors, these summands in the kernel, and this T, the group elements that are generated by these T things, they act as raising and lowering operators between these sectors. Okay, so GC. Okay, these two commute. Okay. GC is isomorphic to the Lie algebra of the automorphisms of VC plus, this kernel, and the isomorphism is by restriction. Let's see, it's hard, yeah, okay. You either put it all the way up or can't see this. I'll try to keep out of the way. G0 is isomorphic to the Lie algebra of the automorphisms of the whole cone that fixed VC pointwise. Okay, so these things obviously can't take you between the sectors. So the idempotents are all, you know, for a particular choice of this decomposition, these particular idempotents are all in one or the other of these. They're all in VC plus. And so if this part obviously can't take you between the sectors because it fixes everything in the sector pointwise, everything in the sum of the sectors pointwise. Yes? Okay, so we're just about done. So the last thing is that the Lie algebra of the stabilizer of E splits as K equals G0 plus K intersect GC. So what's the significance of the stabilizer of E? E is your natural choice for the order unit. Can you see this bottom line? Okay. E is the natural choice for the order unit, and so its stabilizer is a maximal compact subgroup. And so it's actually the reversible transformations, or at least the connected identity component of them. So the point is that these reversible transformations all either fix this thing pointwise or just act as automorphisms within the sectors. Because even if you have two isomorphic sectors here, you can't exchange them with the continuous family of transformations. So that basically is the technical details to some level. Okay, well, thanks.